And welcome back. We're going to finish off Chapter 4 in this lesson. We're going to talk about the last section, 4.6, Modeling with Exponential and Logarithmic Functions. This is really the application problem, the word problem section of the chapter. And we're going to go through some common applications first, and then after that we will do some problems, and then we'll just be done. So, a population that experiences exponential growth or decay, we've teased this for quite a while, changes according to this model, where n equal the population, n sub 0 is the initial population, r is the relative rate of growth. It's growing if r is positive, it's decaying if r is negative. And t equals the time. Notice this is basically the compound, interest compounded continuously formula. Original amount, E, rate of change, and time. And yes, that is a basic exponential growth model, is the interest compounded continuously. But this is just the general one. So, Newton's law of cooling. It's another one. If you have an initial temperature difference between an object and its surroundings, so like if I have a 200-degree cup of coffee in a 60-degree room, then the 200 minus 60 would be a 140-degree difference. So, an initial temperature difference, and if its surroundings have temperature T, then the temperature of the object at time little t is modeled by the function. Ts is the temperature of the surroundings. K is basically just still a relative rate of change. And this is how you calculate pH. You may be familiar with this scale. It measures the acidity of a solution. And if you have a very high pH, it's a base. If you have a very low pH, less than 7, it's considered to be an acid. This is, it just depends on which kind of thing you're doing. I remember my family had a swimming pool for a short period of time, and for that you needed to check the pH to see if it was safe to swim in it at that time, because we had to put lots of chemicals in, chlorine and different things to keep it clean and keep the water clear. And you didn't want to dive in when it was too acidic or too base, because it could give you troubles. You wanted it to be neutral. That's all the theory we're going to look at, so let's do some examples. Alright, we're going to look at problem 11 here on page 395. The graph, I'll go up to the graph in a second, shows the deer population in a Pennsylvania county between 2003 and 2007. Assume that the population grows exponentially. What was the deer population in 2003? Find a function that models the deer population t years after 2003. So, if t is the number of years after 2003, then t equals 0 would correspond to 2003. And that's what the graph shows. At t equals 0, it looks like we have 20,000. So just building our basic equation then, if we're going to build an exponential growth model, remember our exponential growth model is our new amount equals our original amount times e to the rt. Our original amount then, n sub 0, is going to be 20,000. We can use that other point to actually find the other things we need, because now we know n equal 20,000. Well, we know when t equal 4, e to the rt, when t equal 4, n equal 31,000. So 31,000 equal 20,000 e to the 4t, or 4r I should say. Divide out the 20,000, that'll be 31 over 20 equals e to the 4r. This is an exponential equation, so to get rid of the e and get to the exponent, I can take an ln of both sides. ln of 31 over 20 equal ln of e to the 4r. ln of e to the 4r is just 4r. Then divide out the 4. r equal ln of 31 over 20 over 4. This actually answers part A. Part B, find a exponential growth formula. Now we know r, so part B would be n of t equals 20,000 e to the, see, the ln of 31 over 20 over 4. So I'll say that's 1/4 ln of 31 over 20, just for ease. So 1/4 ln of 31 over 20 times t. You can simplify that if you want. If you did a little bit of work on that, you would end up with 20,000 times 31 over 20 to the t over 4. But I don't necessarily know that's a nicer equation necessarily than that for solving, so it's really up to you. How I do that is I'll just work with the e part. You separate out the e to the ln of 31 over 20, and then the t over 4. And then remember, this is equal to e to the ln of 31 over 20 raised to the t over 4 power. Because remember, when you raise something to a power, raise that to a power, you multiply the exponents. Well, this inside then, that simplifies to 31 over 20. So that's how I got that. Okay, what is the projected deer population in 2011? That's easy. You just take, let's see, it's years since 2003, so that would be 8 years. So you just calculate n of 8. So C would just be n of 8. So that would be 20,000 times either one, 31 over 20 to the 8 over 4, or this thing, 1/4 ln of 31 over 20 times 4, e to that power times 20,000. So 20,000, 31 over 20 to the 2. 48,050. Last part, how long will it take the population to reach 100,000? For that, our function equals 20,000 times 31 over 20 to the t over 4. We want to know how long it will take to reach 100,000. So, this is my population over here, so 100,000. See, one more zero. So 20,000, 31 over 20, t over 4. This is an exponential equation since I'm solving for the variable and the exponent. So I isolate my exponential piece, divide out the 20,000. See, that would be 100,000 over 20,000. Get rid of 4 zeros, so it'd be 10 over 2. So yeah, it'd be 5. 5 equal 31 over 20. The t over 4. Trying to get the variable out of the exponent, so I'll take an ln of both sides. Reason I do that is I can bring it out front. T over 4, ln of 31 over 20, ln of 5. So now I just need to multiply by 4, divide by that ln. So t is going to be 4 ln of 5 over ln of 31 twentieths. 4 ln of 5 divided by ln of 31 over 20. So it's going to take about 14, 15 years for the population to reach 100,000. Let's do a Newton's law of cooling problem. We're going to do problem 27 here about cooling turkey. It's almost seasonally relevant. A roasted turkey is taken from an oven when its temperature has reached 185 degrees Fahrenheit and is placed on a table in a room where the temperature is 75 degrees. So, some initial stuff from our Newton's law of cooling formula. You might want to go look that up and write it down on your paper. I'll go ahead and give it here, but I'm just going to erase it in another second. T of T equal Ts plus D sub 0 e to the negative kt. Well, we start writing down relevant information here. Our Ts, our temperature of the surroundings, is 75. The initial difference would be 185 minus that, so 110. Then we want to look at this given information to find the K. So, here's all the information we know. We know the temperature of the surroundings is 75. We know the initial difference is 185 minus 75 equals 110. In part A, it tells us the turkey is 150 degrees Fahrenheit after half an hour. So when T equals 30, we have 150. I didn't actually check to see if they wanted us to get this in terms of hours or not, so let's see. Yeah, we are going to want to be in hours for this one, definitely. So let's set that up using that. So I will say instead of 30, I will say 1/2. All right. So since we know that, we ought to be able to take our basic equation, T of T equals 75 plus 110 e to the negative kt, and plug in these two, so T of 1/2 equals 75 plus 110 e to the negative k times 1/2 equals 150. Take the 75 over. 110 e to the negative k over 2 equals 75. Divide the 110. E to the negative k over 2. Let's see, 75 over 110. Let's see, 5 goes into that 15 times. 5 goes into that 22 times. Take a natural log of both sides, e to the negative k over 2. Whenever you've got a base e, you want to take a natural log just because it will just cancel out. So negative k over 2 equal ln of 1522, 20 seconds. And then k equals negative 2 ln of 15 over 22. We're good. So now we know what the actual formula is. T of T equals 75 plus 110 e to the, let's see, negative k, so 2 ln of 15 over 22 times t. And the other part of problem A asked us to find the temperature of the turkey after 45 minutes. Well, 45 minutes is 3/4 of an hour, so they'd want us to find t of 3/4. So that'd be 75 plus 110 e to the 2 ln of 15 over 22 times 3 over 4. So I'll go ahead and reduce that. That's 2. I'll go away with that, 2. So I just have to take 3 over 2. So I just have to take 75 plus 110 e to the ln of 15 over 22 times 3 over 2. So it's going to be approximately 137 degrees Fahrenheit. And then part B. After how many hours will the turkey cool to 100 degrees Fahrenheit? Now we just set that up. 100 equals 75. So this is part C. I think it's part C. No, part B. Everything else was part A. 100 equals 75 plus 110 e to the 2 ln of 15 over 22 t. By the way, if you wanted to simplify that, you get let's see, e to the, let's see, it would be ln of 15 over 22 time to the 2t, so it would be 15 over 22 to the 2t. If you wanted to rewrite it like this one, I think I'll leave this one just as it is. So 25, 110, e to the 2 ln of 15 over 22 t. Divide out the 110. Let's see, 5 goes in, so that'll be 5 over 22 equals e to the stuff 15 over 22 t. And then take an ln of both sides, so we'll just get ln of 5 over 22 equals 2 ln of 15 over 22 times t. So t equals ln of 5 over 22 times, divided by 2 ln of 15 over 22. So let's see what we get. Ln of 5 over 22 divided by, don't forget to put parentheses around the thing because I have multiple terms, multiple factors down there. 2 ln of 15 divided by 22. So since we're in hours, this is approximately 1.9 hours. Or if you wanted to figure out what that was in minutes, you take off the 1, because we know 1 is 1 hour, and multiply that by 60. So it would be about 1 hour and 56 minutes. Last thing we'll do, I think we'll do a pH problem, just for the fun of it. It is fun. This is going to be 30. An unknown substance has a hydrogen ion concentration of 3.1 times 10 to the negative 8. Find the pH and classify the substance as acidic or basic. Well, I'll probably just do that on the page here. Formula for pH was the negative base 10 log of, and I know I'm in the wrong place, but of the hydrogen ion concentration. So, negative base 10 log of 3.1 times 10 to the negative 8. Well, if you do the work on that, our calculator, probably minimize that somewhat. Well, might as well, it's right there. Negative base 10 log of 3.1 times 10 to the negative 8. So you get about 7.5. That's actually pretty close to neutral. We call that a neutral. Generally, bases are anything really in the top third. 9 and up are really strong bases. That is basic, but it's a very weak base. That should finish us on 4.6, and thus our entire chapter on logarithmic functions. Next time we'll start chapter 5. We're not going to cover all of chapter 5, just 3 sections in fact. 5.1, 5.2, and 5.5. And then that'll be the whole semester. Just as well, since I'm sure we're getting down to the end of it anyway. Unless you're very far ahead, in which case, good on you. Alright. Talk to you then.